Located 120 light-years from our planet, deep within the Leo constellation, a telescope has observed something remarkable. This finding is set to revolutionize our entire perception of extraterrestrial life, with the James Webb Space Telescope having pinpointed a new world, on which the temperature consistently maintains an exact 49 degrees Celsius, 120 degrees Fahrenheit. Its atmosphere, which emanates a chemical fingerprint of living organisms, has led scientists to a 99.7% certainty of their find. A vibrant planet, overflowing with life and seemingly more conducive to existence than our own Earth. Should you be intrigued? Please subscribe and participate in this quest as we bring to light the planetary communications and tales etched among the stars. On a December Tuesday morning, the crucial data appeared, embedded within the light transmissions gathered by the James Webb Telescope. Cambridge University's astrophysicist, Niku Madhusudan, gazed intently at his display, monitoring the subtle variations in light intensity. Having traversed interstellar distances for over a century, each fluctuation served as an indicator, a secret tale conveyed by photons. Following this, an unusual finding emerged. A lone molecule, dimethyl sulfide, which ought not to have been present. Here on Earth, its generation is solely attributed to living organisms, specifically plankton in the seas and bacteria within the ground, and the metabolic activity of myriad invisible life forms. It is not created by volcanoes, lightning, or geological processes. Solely biological mechanisms produce it. Far from being weak, the signal had an error probability of less than 3 in 1,000. Madhusudan's hands shook with thrill. Approximately distant, life was manifesting itself in the vastness of space. The planet K2-18b, responsible for this signal, revolves around a small red dwarf star located in the constellation Leo. With approximately 8 times Earth's mass, it is substantial enough to maintain a profound atmosphere, yet not so large as to transform into a gas giant. For a long time, astronomers presumed these worlds were excessively adverse to life. Their heavy hydrogen layers and intense gravity all suggested an unwelcoming environment. The information from Webb, however, revealed a contrasting picture. Underneath its thick atmospheric layer, the temperature remained stable at roughly 49 degrees Celsius, 120 degrees Fahrenheit, a warmth that is still conducive to liquid water. The hydrogen served as an excellent thermal barrier, capturing heat and spreading it uniformly around the planet. For several months, Madhusudan's group had been examining the planet, recording the subtle starlight that permeated its atmosphere whenever it transited its star. Each such passage brought new revelations, first water vapor, then methane, and subsequently carbon dioxide, a combination of gases that collectively suggested a state of equilibrium and steadiness. And then, dimethyl sulfide appeared, the unequivocal aroma of life. In astronomical research, definitive proof is seldom found. Most findings are tentative possibilities, often invalidated by subsequent information. However, this particular finding possessed a 99.7% confidence, a statistical power usually seen only in the detection of subatomic particles or gravitational waves. Humanity, for the first time, was not simply hypothesizing. We were nearly convinced about the planet's substantial atmosphere. It operates as a global greenhouse, yet without being detrimental. Instead of accumulating damaging warmth, it generates a state of thermal stability. Water neither solidifies nor boils. It simply endures, immense, profound, and constant. This kind of world would be a chemist's dream. Life would not have to struggle against dry spells or cold snaps. Evolution would be free to advance without interruption, much like a ceaseless tune. Its primary star glows dimly compared to our sun, being small, consistent, and virtually eternal. Red dwarf stars endure for trillions of years. Their luminosity is gentle yet everlasting. In the vicinity of such stars, time itself becomes abundant. Any nascent biological spark originating there could possess an inconceivable span of time to develop, adjust, and evolve. Upon the revelation of the initial findings, the global scientific community paused. For many decades, our quest had been for an Earth-like counterpart, a terrestrial world circling a yellow sun. Nevertheless, what emerged was something completely distinct and in some ways even more conducive to supporting life. This wasn't merely an Earth-like entity. It represented a novel class of life-sustaining planet. Expansive seas under unfamiliar heavens, with existence maintained not through similarity to humanity, but by the cosmos's inherent inventiveness. Observing such a celestial body necessitated Webb achieving extraordinary feats. Positioned a million miles from Earth at a Lagrange point known as L2, the observatory resides in perpetual shadow. Its five-layered solar shield, comparable in area to a tennis court, maintains its temperature below that of Pluto's surface. A total of 18 gold-coated mirrors, each a flawlessly geometric hexagon, gather light imperceptible to human vision. Collectively, they form a mirror of such accuracy that it can sense the thermal signature of a bumblebee on the lunar surface. As that remote world passes before its star, a small portion of starlight permeates its atmospheric layers. Atmospheric molecules absorb particular wavelengths, leaving subtle traces, a unique spectral signature. Through the interpretation of these patterns, Webb uncovers the planet's chemical composition. This process is akin to recognizing a voice by its exhalation. However, discerning that faint signal presents an immense challenge. The parent star outshines its orbiting planet by billions of magnitudes. To counteract this, Webb employs its coronagraph, a device designed to obscure the star's intense luminosity. Similar to obscuring the sun with your thumb to spot a nearby firefly, the residual starlight undergoes filtering, analysis, and noise reduction by exceptionally accurate algorithms. These algorithms are capable of distinguishing a few significant photons from millions of inconsequential ones. Such photons bear narratives predating recollection. Each departed its native world 120 years prior. Approximately when humanity initially mastered transmitting radio signals into space a century ago, this data now indicates that life was already flourishing on another world. It's a humbling realization that we are not witnessing life's genesis, but rather its past state, a 100-year-old reverberation from a vibrant planet where existence has probably persisted uninterrupted. The atmospheric composition unveiled more than just chemical makeup. It disclosed dynamic processes. Methane, carbon dioxide, and water vapor maintained a fragile equilibrium, a form of global metabolic activity. In a world devoid of life, these gases would rapidly interact and settle into a stable chemical state, yet Webb observed no such equilibrium. Instead, the proportions varied, indicating a state of chemical imbalance, the identical characteristic found in Earth's life-supporting atmosphere. Life inherently prevents stasis. It perpetually modifies its surroundings through respiration, ingestion, and expulsion. Even the absence of certain gases on the planet conveyed information. Had it been barren, its atmosphere would be saturated with ammonia. However, ammonia was nearly completely missing, suggesting an active process was consuming it, transforming it, and purifying the atmosphere. On Earth, microorganisms perform precisely this function. The more in-depth the examination, the more distinct the understanding became. It was not an inert world, but a flourishing one, not a mere chemical anomaly, but a planet-wide ecological system. From a statistical standpoint, the certainty was compelling, a 3 sigma observation indicating a 99.7% probability, which translates to an approximate 1 in 1,000 likelihood of error. In virtually any other discipline, such a finding would be indisputable, yet no mere figure could fully convey the profound implications of this discovery. For hundreds of years, we had pondered the existence of extraterrestrial life. Now, for the very first time, the response was not conjecture. It was empirical data. To arrive at this conclusion, Webb needed to identify molecular signatures present at concentrations of merely a few parts per billion. A spectral signal, akin to detecting a heartbeat through a hurricane lamp, was quantified with an accuracy of 1 part in 10 million. Every recorded wavelength underwent comparison, and all alternative explanations were systematically dismissed. Terrestrial contamination was deemed impossible. Statistical analysis showed random noise to be negligible. Thus, the most straightforward and sole explanation pointed to biological origins. Consequently, upon the data's confirmation, every scientist reviewing it experienced an identical, profound realization. This was more than merely an exoplanet. It signified the conclusion of cosmic isolation. The planet's immense oceans, extending hundreds of miles deep, indistinctly merge the boundary between water and atmosphere. This water combines with hydrogen, forming a liquid that maintains stability across an astonishing spectrum of temperatures. This unique chemistry might foster life forms unimaginable to us, organisms that respire hydrogen rather than oxygen. These beings subsist on methane rather than solar energy. Beneath its ceaseless cloud cover, pressure intensifies to levels we can scarcely replicate. Diamonds might materialize and descend through the atmosphere, sparkling into the oceans akin to solidified stars. Somewhere beneath that radiant mist, within the warm, dimly lit waters, life is almost assuredly active, neither delicate nor transient. Instead, it is ancient and plentiful. This understanding fundamentally alters everything. If biological entities can flourish in hydrogen-rich oceans, orbiting a red dwarf star, then life is not uncommon. It is unavoidable. 75% of the stars within our galaxy are red dwarfs, calm, long-lasting suns possessing planets identical to this one. Should even a small portion of these harbor biospheres, then our Milky Way galaxy teems with inhabited worlds. This finding redefines the concept of habitability, indicating that life does not necessitate an Earth-like duplicate. It merely requires equilibrium, the appropriate chemistry, the suitable temperature, and sufficient time. Webb's golden mirrors accomplished more than mere observation. They linked us to an additional phase of creation. Every photon it captured conveyed a faint murmur across the expanse of space and time. The exhalation of an invisible ocean, the subtle indication of life beyond our grasp. Within that dim illumination, humankind discovered evidence that existence is communal. That we are neither the initial nor the sole, and assuredly not the final. The cosmos, it appears, has sustained life for a duration exceeding our logical comprehension. The red dwarf star central to this system is sufficiently compact to be contained within Jupiter, yet possesses enough density to retain a planet such as K2-18b within its gravitational pull indefinitely. Its illumination is faint, resembling a deep reddish ember instead of our sun's intense white. For human observers, it would not radiate intensely. Instead, it would emit a gentle, steady, and enduring glow. This is not a star characterized by a rapid existence and early demise. Rather, it combusts gradually, almost delicately, extending its lifespan not merely into billions but into trillions of years on a cosmic scale. It approaches immortality. That extended lifespan alters everything surrounding our sun. Illumination fluctuates, climates become unstable, and one extinction event follows another. Yet, in this location, the light remains constant, providing identical warmth across countless centuries and millennia. No violent flares exist to strip the atmosphere, nor any chaos to undo chemical processes. For a world such as K2-18b, this unwavering consistency signifies something extraordinary. Oceans that never freeze, clouds that never dissipate, and boundless time for life to emerge, adapt, and persist. For many decades, scientists dismissed red dwarfs as unsuitable for sustaining life. They are small, cool, and their habitable zones are situated so intimately that any planet must orbit in very close proximity to the star. However, what was once perceived as perilous has proven to be ideal. K2-18b completes its orbital year in merely 33 Earth days. Positioned near enough to absorb the heat of its faint star, yet sufficiently remote to stay tranquil. One hemisphere consistently receives illumination. The opposing side rests in shadow. Viewed from orbit, it would resemble a luminous sphere, partially immersed in a deep red glow, partially enveloped in gloom, yet even that unlit hemisphere does not experience frigid temperatures, owing to the world's dense hydrogen-rich atmosphere, which functions as an extensive heat transporter, distributing thermal energy throughout its heavens. Such consistent equilibrium is seldom found throughout the cosmos. It grants water-lasting existence, permits atmospheric conditions to progress calmly, and offers a tranquil environment for chemical processes. Should organisms inhabit this place, they develop under a star that neither ascends nor descends, a planet suspended in an eternal twilight, where the boundary separating light from darkness functions not as a border, but as an environment for life within that perpetual crepuscular glow. The heaven's hue would never appear azure. Instead, it would radiate in strata of deep red, purple, and bronze, faint yet ceaseless. The celestial body would remain suspended, unmoving, above the skyline, permanently anchored in that single position. The aquatic expanses beneath would mirror that reddish illumination, emitting a soft luminescence as undulations ripple beneath a hazy, indistinct horizon. On the nocturnal hemisphere, complete obscurity would not prevail. The thick atmosphere would disperse the star's radiance, imbuing the gloom with subtle metallic tints. Even in that region, illumination would persist. The luminescence of polar lights, the flicker of electrical discharges within remote cloud formations. This world is not characterized by stark differences, but rather by gradual transitions, one where all elements change fluidly without suddenness. Should life's development have commenced here, it proceeded with deliberation. On our planet, life's trajectory was molded by catastrophic events, collisions, glacial periods, and abrupt fiery eruptions. However, in the vicinity of this tranquil star, mass extinction events are absent, as are abrupt terminations. The temporal pace is more deliberate, and the scope of existence is more expansive. Organisms on this world could mature unimpeded, propelled by the gentle exhalation of a red dwarf's perpetual morning. The Webb telescope's apparatus was specifically designed to observe. Within this specific type of illumination, infrared, which is precisely the wavelength red dwarfs radiate with the greatest intensity, this factor rendered K2-18b's distinct characteristics so discernible. The telescope wasn't struggling to discern a faint object. Rather, it was precisely calibrated to the star's inherent communication, with each infrared ray containing the atmospheric composition of the planet, the warmth emanating from its clouds, the fragrance of its seas, and the exhalations of its undiscovered life. Every instant the planet transited its star, a minute portion of the stellar light permeated its atmosphere. Atmospheric molecules absorb that illumination at specific wavelengths, creating subtle indentations, spectral signatures, which the telescope deciphered as a chronicle composed of light. These records revealed the presence of water, methane, carbon dioxide, and ultimately dimethyl sulfide, which serves as an indicator of life. For human observers, the red dwarf would seem ordinary, almost imperceptible in the night sky. However, its very lack of brightness facilitates detection. Observing planets is simpler around smaller stars, as their reduced glare results in clearer signals. What appears feeble is, in reality, ideal. Red dwarfs are not hindrances, but rather celestial magnifying lenses, unveiling the subtle indications of their orbiting worlds. If one were to stand on one of K2-18b's elevated plateaus and gaze skyward, the panorama would be dreamlike. The horizon would arc under a bronze-hued firmament, and the atmosphere would visibly vibrate with warmth. The solar illumination would feel gentle, resembling warmth more than intense brightness. Shadows would extend, appearing elongated and unhurried, extending endlessly. The distinction of day and night would vanish, superseded by gradual alterations in hue, in temperature, and in the very pulse of the planet. Life, if present, would manifest distinctively. Flora might appear deep black, indigo, or profound violet, absorbing every errant photon of red light. Photosynthesis would proceed at a gradual yet consistent pace. Organisms that consume them might perceive their environment through vibrational pressure instead of visual input. Nothing would be rushed. Energy is limited, yet time is boundless. Evolution would favor patience over swiftness and resilience over hostility. The red dwarf's most significant attribute is its temperance. It burns with discipline, never squandering energy nor experiencing sudden surges. Whereas our sun will expand and expire within 5 billion years, K2-18's parent star will still be emitting a gentle radiance. Even after the Milky Way has transformed beyond recognition, for the life orbiting it, the term apocalypse carries no significance. When the telescope's instruments registered light from K2-18b, that illumination had already been in transit for 120 years at the commencement of its voyage. In 1905, on Earth, Einstein was developing his theories of relativity while the Wright brothers conducted flight tests. Our kind had only just mastered the ability to fly, yet that distant world had already existed for ages beneath its own atmosphere. This implies that what we perceive is not the current moment, but rather a bygone era, a recollection of a vibrant world as it existed 100 years ago. Even when we observe it again many decades hence, we will still be perceiving that same past instant. Astronomy consistently represents a dialogue spanning different eras. The cosmos communicates at a leisurely pace, yet even a faint signal originating 120 light-years distant possesses the power to fundamentally alter all our convictions. The atmospheric composition there, the specific blend of gases, and the disequilibrium that only living organisms are capable of sustaining. It moves in harmony with the consistent pulse of its sun. The red dwarf offers an unvarying tempo, and the planet responds through its metabolic processes. Collectively, they establish an ideal cycle, with one element being stable and the other vibrant. This represents a connection between contrasting entities. A harmonious interplay between combustion and respiration. The star offers stability, while the planet introduces variation. One consumes, the other revitalizes. Our home planet originated amidst turmoil, characterized by intense heat and collisions, reflecting the ferocity of a nascent solar system. However, orbiting a tranquil red dwarf, existence might commence serenely. The luminosity is dim, yet for a world such as K2-18b, it suffices, providing ample warmth for liquid water bodies. Sufficient illumination for chemical reactions and ample duration for all processes to unfold. This, perhaps, constitutes the universe's understated reality. That living organisms do not seek intense brightness, merely equilibrium. That they can flourish beneath ruby-red heavens just as readily as under azure ones. That life itself possesses adaptability, universality, and patience. Therefore, when we gaze towards the constellation Leo and perceive that subtle reddish glimmer, we are not observing a void. We are witnessing resilience, a star that has been gently radiating for countless millennia and is destined to continue doing so for trillions of years further. And beneath its tranquil radiance, obscured by veils of hydrogen and vapor, a vibrant planet could potentially still reside, revolving gradually and quietly within the illumination of an everlasting stellar body. The light emanating from K2-18b's crimson star passes through strata of hydrogen and atmospheric moisture prior to descending into the underlying oceans. For human observers, those heavens would not appear azure. Instead, a faint amber hue transitioning to a profound rose color close to the skyline. Clouds meander unhurriedly, expansive and thick. Colored by the star's subtle coppery radiance, the atmosphere itself would undulate, feeling substantial, opulent, nearly incandescent. This atmosphere, a vibrant gaseous lens, acts as the planet's primary architect, both safeguarding and nurturing everything below it. Unlike Earth's delicate and thin atmosphere, this one is immense and dense, extending for hundreds of kilometers, primarily composed of hydrogen intermingled with carbon dioxide. Methane and water vapor combine to form a potent greenhouse effect, though it is not a harmful one. Rather than incinerating the surface, the warmth disperses uniformly, maintaining the planet in a state of thermal balance. Water neither solidifies nor vaporizes. Instead, it persists, circulating through perpetual cycles of evaporation and precipitation. When viewed from orbit, the higher strata seem tranquil, but further below, the air becomes sufficiently dense to obscure the distinction between the atmosphere and the ocean. Clouds blend into mist, and mist then dissipates into the ocean. The interface between air and water is not a distinct surface. Instead, it's a gradual transition, one slowly merging into the other. Beneath that gentle shroud, sunlight diminishes, giving way to a crimson luminescence that permeates. Similar to light passing through stained glass, the ocean itself could extend for hundreds of kilometers in depth, reaching pressures far exceeding what our submersibles could withstand. Hydrogen readily combines with water, forming a unique liquid unlike any found on Earth. This substance is less dense, more easily compressed, and maintains its fluidity across a vast temperature spectrum. It represents an ocean where chemical processes are paramount. This environment serves as a breeding ground for molecules capable of assembling, dividing, and respiring. Should life exist there, its origins are probably in those deep regions, beyond the penetration of light. On our planet, we formerly believed sunlight was indispensable for life's emergence. However, in the abyssal depths of Earth's oceans, close to volcanic vents, we discovered complete ecosystems flourishing in perpetual darkness, sustained by chemical reactions instead of light. These organisms subsist on warmth and minerals, utilizing energy gradients rather than solar radiation. A similar scenario might unfold on K2-18b. Its oceans might contain hydrothermal zones where hydrogen and carbon intermix, potentially igniting the initial spark of biological life. The immense pressures in those depths would pulverize steel, yet for biological cells, such pressure can offer safeguarding. It helps stabilize delicate molecules, propels chemical reactions, and ensures water remains in a liquid state even at elevated temperatures. Should microorganisms have ever established themselves in those deep regions, evolution would have benefited from billions of tranquil, consistent years to refine them. While Webb's instruments cannot peer so far beneath the clouds, the overlying atmosphere reveals clues about the activity below. The gases identified, methane, carbon dioxide, and minute quantities of dimethyl sulfide, indicate a dynamic cycle linking the ocean and the atmosphere. On Earth, living organisms uphold this equilibrium. Algae generate methane, microbes consume it, and plants release oxygen. On K2-18b, a comparable process might be occurring, albeit governed by distinct principles. The lack of ammonia provides an additional hint. On lifeless planets, ammonia typically accumulates over extended periods. This substance, a remnant of chemical decomposition, is absent here. It is probably transformed into more intricate compounds or broken down through biological metabolic processes. Even without direct observation of any organism, the atmosphere appears to be continuously regulated, optimized, and revitalized. Picture yourself standing, or possibly suspended, within that setting. The surrounding air would possess sufficient density to feel like water. Sound would propagate sluggishly yet distinctly, with vibrations traversing the fluid medium in profound, resonant undulations. Even a solitary drop of this ocean would exert greater pressure than the deepest point of the Mariana Trench. Nevertheless, for indigenous life, it would seem normal and stable. Tranquil light would rapidly diminish with increasing depth. Just a few hundred meters down, the environment would become a reddish-black. Its illumination would come solely from subtle chemical luminescence, representing life's inherent response to the absence of light. Conceivably, minute organisms might drift there, emitting a gentle glow, communicating through exchanges of warmth and light. Alternatively, vast, deliberate beings could traverse the warm chasm, perceiving each other via electric fields and pressure fluctuations. Each interaction within that ocean would represent dynamic chemistry. Methane ascending from the deep would combine with carbon dioxide from higher up, generating novel compounds that sustain microscopic organisms. Hydrogen, dissolved within the water, would function as both a protective element and an energy source. On Earth, this kind of chemistry forms cells. However, here it could create something more unusual, a form of biology entirely independent of oxygen. Nevertheless, in numerous aspects, it would retain a sense of familiarity. Life, wherever discovered, exhibits equilibrium. Energy circulates and refuse transforms into sustenance. Continuous alteration ensures stability. This is precisely what Weber observed in the gas proportions far above the planetary clouds. A self-regulating biological system operating within the atmosphere's middle strata. The temperatures and pressures are comparable to those found close to Earth's surface. Should any region of K2-18b be capable of supporting life forms akin to our own, that would be the location. Small microbial groupings could float on air currents, much like plankton suspended in an unseen ocean, consuming minute chemical traces and drawing energy from the red sun's light. Every single one would represent a minute particle of existence, born by the breezes, ascending and descending within a global atmospheric ocean. We are already aware that similar environments can be found within Venus's clouds. Researchers have identified chemical signatures suggesting the presence of microbes suspended far above the surface. K2-18b's atmosphere is considerably milder, lacking acidic tempests and oppressive heat, thereby presenting an even more promising environment for airborne organisms. If the underlying oceans constitute the planet's heart, then its atmosphere serves as its respiration. Each molecule of methane or dimethyl sulfide released from the ocean transforms into a communication, ascending towards the starlight. These molecules traversed the void and reached our instruments, bearing the distinct metabolic rhythm, the very heartbeat of an extraterrestrial biosphere. The remarkable aspect of this finding is our ability to decipher this information without ever departing our own world. From our tranquil planet orbiting our sun, we can, solely by analyzing light, reconstruct the climate, chemistry, and potentially the biology of another world, based on the most minute infrared beam distortions. We are able to discern if another ocean exhibits waves or if another sky contains precipitation, and indeed, it certainly does. Within K2-18b's atmosphere, water vapor coalesces into enormous clouds that ascend and descend through gradual convective processes. Upon cooling, these clouds discharge precipitation that descends not as individual droplets, but as sheets as dense as fog. They drift through the atmosphere until they disappear into lower strata, where the atmospheric pressure is exceedingly elevated. Consequently, the precipitation might transform into molten metal or solid ice prior to descending into the underlying ocean. Each phase of water vapor, liquid and solid, could coexist concurrently, arranged in strata resembling the chapters of a universal narrative, where the process of evaporation, condensation, and rainfall mirrors the very cycle that sculpted Earth's climate and sustained its life forms. This serves as a testament that, even across vast cosmic distances, nature's fundamental principles are ubiquitous. Chemical processes adhere to identical rules throughout the cosmos. The more extensively researchers investigate, the more apparent it becomes that K2-18b is not merely theoretically capable of supporting life, but is practically dynamic. The planet respires, it reprocesses, it transforms. Every fresh observation uncovers movement, interconnected responses, and adaptation, all characteristic signs of a vibrant system. Somewhere beneath the cloud cover, within the compressed warmth of those extraterrestrial oceans, evolution might have already produced extraordinary configurations. Basic cells could have coalesced into colonies, and these colonies might have developed the capacity to perceive, to locomote, and to cogitate, all at a rate quantified not in millions but in billions of years. The red dwarf's deliberate rhythm permits evolutionary processes to progress unimpeded. We probably won't observe them firsthand, not at this moment, yet the atmosphere they emit, the particles they discharge, have already arrived here. Minute indications of being transported through the void. They demonstrate we're not merely cosmic onlookers, but active participants in its most ancient dialogue. The interplay of illumination and vitality. While the James Webb Telescope keeps observing this planet, each light particle it records advances our comprehension of what's hidden. The subsequent phase involves charting the atmospheric strata with even greater precision to gauge light variations, wind patterns, and chemical transformations annually. However, for the present, this knowledge suffices. Deep below a scarlet sun, under clouds that gleam like satin, and boundless oceans, a state of balance exists. A dynamic stability between warmth and chill, atmosphere and water, celestial body and world. This equilibrium is so flawless, it nearly appears deliberate, not engineered but unavoidable, as if the cosmos inherently pursues existence wherever possible. And on K2-18b, it might have discovered one of its most lasting abodes, a planet gently respiring under a red sun's glow, a world whose seas recall creation's initial warmth and whose firmament bears life's calm, consistent rhythm. For hundreds of years, humankind has gazed skyward and perceived only stillness. Subsequently, K2-18b emerged, not the Earth's counterpart we anticipated, but something more enigmatic, a water-covered planet enveloped in hydrogen. It revolves around a red star, distant from any place we've ever considered home. Its finding didn't merely broaden astronomical understanding, it broadened imagination itself. For the reason that, historically, we're no longer simply questioning if life exists beyond Earth, we are observing indications that it does. When Webb's gilded reflectors disclosed subtle evidence of dimethyl sulfide, it transcended mere information. It represented a significant shift in the human narrative. Within a few spectral lines, the cosmos's quietude broke open. Not audibly, but with proof that one molecule spanned a divide separating planets. It conveyed softly yet clearly, "You're not solitary." The significance of this cannot be quantified by percentages or certainty ratings. Its impact extends beyond scientific realms into philosophy, artistic expression, conviction, and self-perception. It compels us to view life not as an anomaly, but as a fundamental rule. For many generations, we believed existence was uncommon, that biological forms were a celestial fluke resulting from ideal circumstances. However, Earth has never been the sole arena where chemical principles unfold. These laws have been active throughout the galaxy for eons, wherever material achieves equilibrium between power and structure. We've already observed clues: microorganisms flourishing in radioactive refuse, bacteria dormant for thousands of years under Antarctic glaciers, and organisms dwelling miles beneath the sea. They sustain themselves not by solar radiation but by the planet's own warmth. Life, it appears, does not require ease. It flourishes despite adversity, and currently, 120 light-years distant, a planet exists beneath a red star. Evidence that being is not delicate. If K2-18b supports life, it fundamentally alters everything. This is because red dwarf stars, similar to its primary star, represent the most prevalent suns within the Milky Way. For each star resembling our own sun, there exist 1,000 such stars, which are smaller, more ancient, and more stable. If even a small percentage of these possess planets akin to K2-18b, then the cosmos is not quiet. It is abundant with billions of planets, billions of origins. The ramifications extend well past astronomy. They delve into the precise formula, attempting to quantify our isolation in the universe. The Drake equation, which for many decades served as a conceptual exercise, a tenuous effort to estimate the number of intelligent societies that could currently exist. Now, one of its most ambiguous factors, the probability of life arising, has transitioned from an unknown to an almost definite fact. Life, it appears, does not necessitate Earth-like environments. Life manifests itself whenever chemistry and time are afforded the necessary conditions to operate, provided biology can utilize hydrogen. Should oceans be capable of existing beneath red suns, then the very definition of what is considered habitable expands to become nearly universal. This transforms our perception of ourselves, as for the majority of human history, our narratives positioned us as central and specially chosen. We were singular, enveloped by a sacred void. Subsequently, Copernicus relocated Earth from the core of creation, followed by Darwin, who situated humankind within nature rather than above it. Presently, the Webb telescope has transitioned life itself from the realm of miraculous phenomena to the rhythm of physics. We are not an anomaly. Rather, we are a manifestation, a single stanza in an anthem that commenced well before our time and will persist long after. Nevertheless, this understanding does not lessen our significance. Instead, it links us, implying that the very atoms comprising our bodies, having been forged within dying stars, could potentially respire and cogitate in other locations. The identical chemical processes coursing through our veins might also be present in extraterrestrial oceans. The identical physical laws that sparked our sun illuminate countless other stars. The James Webb Space Telescope has emerged as a novel sensory apparatus for us, Not merely visual or auditory, but something more profound, a method for discerning life by means of light. Every photon it registers represents a fundamental unit in the lexicon of existence, journeying for more than 100 years to arrive at our location. It does not conduct its quest in isolation. Additional observatories, including the Nancy Grace Roman Telescope, Ariel LUVOIR, and forthcoming colossal ground-based instruments, are currently under construction to persist in this exploration. Before long, we will possess the capability to scrutinize not merely a single planet, but hundreds. Should even a small number exhibit identical chemical discrepancies, the same subtle indications of metabolic activity, then life ceases to be a miraculous occurrence. Instead, it is a recurring pattern. Envision the evening when we comprehend that every constellation conceals a vibrant world, each dim star serving as a sun possessing its own oceans, atmospheric formations, and chemical composition. A portion of these worlds might be rudimentary. Conversely, others could be unimaginably ancient, their respective civilizations having emerged and then collapsed prior to the initial human efforts in stone carving. However, even if direct contact is never established with them, their mere existence fundamentally alters the significance of our own, due to the unprecedented realization that we are aware that extraterrestrial life is considerably more attainable than previously imagined, a profound implication for both philosophical inquiry and religious belief systems. This revelation recontextualizes all aspects. Should life permeate the galaxy, then the act of creation itself is not discriminatory. It is prolific. The concept of the sacred transforms from a singular event confined to one location into a phenomenon that occurs universally. Material substance self-assembles. The true marvel is not the presence of life on our planet, but rather the universe's capacity to permit its existence across all locations. Nevertheless, this disclosure presents a reflective aspect. We have uncovered evidence suggesting that life can flourish beneath extraterrestrial heavens, whereas our own world, situated beneath a luminous yellow star, falters under the burdens of our own creation. In contrast, K2-18b exhibits equilibrium, stability, and resilience. Our planet, Earth, appears turbulent and delicate when contrasted. The cosmos has demonstrated to us the true nature of sustainability. Entails, not as a mere political aspiration, but as an inherent principle of nature. Conceivably, this constitutes the profound insight offered by K2-18b. The continued existence hinges not on dominance, but on balance. Life persists most effectively not through conquest. However, when this collaboration succeeds, future historians, reflecting on the past, might label this particular juncture. When the field of astronomy transitioned into biology, as we ceased examining light and commenced investigating life by means of it, the Webb telescope's golden mirrors, suspended in the vacuum of space a million miles distant, have transformed into conduits connecting our tiny blue planet to something immense and everlasting, for even at this very moment as Webb gathers data, our own transmissions are propagating outwards. Radio transmissions, television signals, and the digital pulse of our society are all spreading across the cosmos at light speed, traversing the expanse to K2-18b and further. Conceivably, if that celestial body genuinely supports life, our transmissions might have already reached it. And possibly, upon its reddish landscapes, some living entity is paused, detecting a subtle pattern, a cadence within the background noise. A clear indication that it, too, is not solitary. Should that instant ever materialize, if two planetary bodies divided by 120 light-years acknowledge one another's existence, it could represent the most significant exchange throughout history, not through spoken words or auditory signals, but rather via light. Until that time, the revelations from Webb are sufficient, enough to comprehend that the cosmos is not devoid of sound, but instead filled with concealed melodies. It's enough to grasp that life is not delicate, but rather an unavoidable outcome. Sufficient to recall that each air molecule, every ocean droplet, and every inhalation we make links us to something more ancient and grander than ourselves. As the Webb telescope persists in observing the darkness, gathering the most subtle murmurs, From extraterrestrial oceans and atmospheres, we start to apprehend the reality that has patiently awaited our discovery for such an extended period. The universe is vibrant. The finding on K2-18b signifies not a conclusion, but a fresh start, the initial quantifiable indication that existence might not be restricted solely to Earth. From this point onward, the inquiry transforms. We cease questioning whether life is present elsewhere, but rather the multitude of forms it could assume and its potential reach. Scientific understanding is already evolving. For the first time, astronomy, chemistry, and biology are converging into a unified field of study, a quest for the characteristic patterns that delineate life throughout the galaxy. Investigators refer to this as comparative astrobiology, which involves examining atmospheres, climatic conditions, and chemical compositions as an interconnected framework. Planets are no longer merely isolated specks of illumination. Instead, they are transforming into data points within a dynamic cosmic chart. Here on Earth, novel laboratories are replicating the environments found on extraterrestrial planets. Pressurized enclosures simulate the thick hydrogen atmospheres characteristic of sub-Neptune worlds. These experiments investigate the behavior of carbon, nitrogen, and water when subjected to temperatures and pressures not encountered on our planet. Certain experiments extend over several months, observing molecules as they develop into intricate organic substances that might eventually aid in elucidating the genesis of life across the cosmos. Other investigations concentrate on equilibrium chemistry, seeking the precise juncture where fundamental physics transitions into metabolic processes. The objective is to compile a comprehensive library of biosignatures, essentially a catalog detailing the true appearance of living atmospheres. Irrespective of their chemical makeup, artificial intelligence is progressively emerging as the primary interpreter for this emerging field of astronomy. Machine learning algorithms, having been trained with data from the Webb telescope, are capable of discerning molecular patterns, imperceptible to the unaided human eye, such as subtle gas mixtures and periodic seasonal shifts, along with minute luminosity variations that could signify atmospheric conditions or biological proliferation. Processes that previously demanded months of human analytical effort are now completed in mere minutes. Every subsequent dataset further hones these algorithms, instructing machines to discern the most minuscule chemical pulse amidst the immense cosmic background noise. Orbiting Earth, a fresh cohort of telescopes is gearing up for subsequent advancements. The Nancy Grace Roman Space Telescope, scheduled for launch within this decade, is set to discover thousands of exoplanets and conduct the initial comprehensive survey of their classifications and orbital paths. Europe's aerial mission will subsequently embark on a detailed examination of the atmospheres of 1,000 of these celestial bodies. Terrestrially, the extremely large telescope situated in Chile will integrate adaptive optics with colossal mirrors to ascertain the isotopic composition of remote planetary atmospheres. These delicate proportions can indicate whether a planet's atmospheric gases originate from geological processes or biological activity. Collectively, these observational facilities will establish an interconnected system, a comprehensive planetary reconnaissance network, transforming far-off luminous points into quantifiable, comparable celestial bodies. The subsequent major advancement will not pertain to data volume, but rather to observational capability. Engineers are devising innovative optical instruments, including coronagraphs and deployable star shades, designed to obscure a star's luminosity so thoroughly that the faint reflected light from its orbiting planet becomes discernible. Even a single pixel of this light can disclose information about its color, cloud coverage, and rotational period. Given a sufficient number of pixels, we could eventually discern continents or oceans shimmering beneath an extraterrestrial sun. Mission concepts such as NASA's HabEx and LUVOIR could render this achievable within a few decades. These advanced telescopes would not merely identify the chemical signatures of life, but also monitor its climate dynamics, observing seasonal changes, atmospheric disturbances, and the gradual cadence of alien meteorological phenomena. Further ahead in time, an alternative concept is materializing, employing the sun itself as a telescopic instrument from a particular vantage point, situated over 550 times the Earth's distance from the Sun. At this location, gravity causes light from remote stars to converge, thereby forming what physicists refer to as the solar gravitational lens. A compact probe dispatched to that region could harness this phenomenon to achieve a billion-fold magnification of a planet, enabling the resolution of features as minute as mountain ranges. While attaining such a vast distance would necessitate several decades, the underlying technology remains within the capabilities of contemporary 21st century engineering. Concurrently, as telescopes conduct observations from remote locations, propulsion research is focused on advancing towards the subsequent frontier, which involves not merely observing other celestial bodies, but actually journeying to them. Initiatives such as Breakthrough Starshot envision swarms of laser-propelled nanocraft. Moving at one-fifth the speed of light, their initial destinations will be proximate stars, for instance, Alpha Centauri. However, these identical techniques might ultimately dispatch tiny probes to celestial bodies akin to K2-18b. Closer to our planet, novel propulsion systems, including fusion drives, sophisticated ion engines, and solar sails, are currently undergoing development and rigorous testing. Through missions spanning our solar system, every deep space navigation experiment, and each trial of autonomous control advances the technology for interstellar travel closer to becoming a reality. Nevertheless, the future implications of this finding is not merely concerned with distance. It also involves grasping its full meaning, as an increasing number of planets exhibit chemical traces, which hint at life. Researchers will then commence studying not isolated cases, but rather the statistical prevalence of existence. What are the preferences of life? Crimson or golden stars, profound oceans or superficial seas, solitude or intricacy? Before this century's midpoint, the investigation into life beyond Earth might no longer revolve around infrequent discoveries. Instead, it will be about recognizing patterns in biology observed on a galactic scale. This understanding will not be restricted solely to astronomy. The identical models utilized for comprehending other celestial bodies can assist us in safeguarding our own. Investigating atmospheric equilibrium on other planets refines our comprehension of climate feedback on Earth, how atmospheric gases stabilize temperatures, how oceans govern heat, and the inherent fragility of equilibrium. By understanding how other planets sustain life, we might discover methods to keep our own alive. The ramifications extend even more broadly. Should we confirm the existence of life beyond Earth, even rudimentary microbial forms, it will fundamentally redefine the ethical framework governing exploration. The 1967 Outer Space Treaty was formulated prior to the possibility of such discoveries. Its purview is territory, not biological entities. Novel policies will be necessary to shield extraterrestrial ecosystems from contamination and exploitation, thereby ensuring that contact signifies cooperation rather than consumption. For the very first time, space law might be compelled to acknowledge the inherent rights of life itself, regardless of its diminutive size or unfamiliarity. This quest, extending beyond legal and scientific realms, will fundamentally reshape how civilization perceives itself. For many centuries, humanity has envisioned the cosmos as a grand stage for human advancement, an immense void poised for exploration. However, as mounting evidence suggests the existence of life elsewhere, that narrative transforms. The universe no longer serves as a mere backdrop. Instead, a collective, an interconnected web of vibrant planets, all molded by the identical forces that formed us. Our objective might evolve from domination to communion, from extending our reach to safeguarding what exists. Children arriving in future decades will mature with the knowledge that the nocturnal heavens hold sound, as each star they observe potentially harbors oceans, an atmosphere, and the gradual pulse of life. Their cosmic charts will not conclude with our solar system, but will organically stretch throughout the vibrant galaxy. The query that characterized many generations, "Are we solitary?" will recede into the past, superseded by a fresh inquiry. How do we integrate into this expansive biological network? For the present, the endeavor proceeds without fanfare. Every fresh observation contributes a detail to the narrative. Every subsequent mission broadens our scope. Information will gather until undeniable patterns emerge. And beyond those figures, amidst the dim radiance of crimson stars and far-off seas, we shall ultimately perceive our own existence. Not merely as onlookers, but as active contributors to the identical cosmic process. K2-18b offered the initial subtle hint. More will come after. Each will serve as a reminder that existence isn't a unique marvel, but rather a repeated motif within the universe's lexicon. The subsequent telescopes we construct will not only peer further, but will also listen more acutely, attuned to the subtle melodies of biological chemistry. Throughout the expanse of space and time, the forthcoming era of exploration will be gauged not by distance or even light years, but by comprehension, by the profundity with which we apprehend the connection between our planet and all that lies beyond. And when the subsequent signal arrives, when an additional world is added to the expanding catalog of inhabited places, we will identify it immediately, having acquired the skill to interpret the indicators, not as remote marvels, but as manifestations of a common genesis. The quest will genuinely be unending. Every solution will reveal a new vista. Each finding will pose a further query. Yet this is the essence of exploration. Not attaining the limit of the undiscovered, but perpetually broadening its scope. And within that broadening, we start to perceive the authentic future, a society that views itself not as the cosmos's focal point, but as an element of its vibrant periphery. Ultimately, finding something new frequently resembles less of an unveiling and more of an acknowledgement, a faint reverberation of knowledge we already possessed. For hundreds of years, we gazed at the nocturnal heavens, pondering who else might exist. Now, as we observe, we grasp they were perpetually present. We simply hadn't learned to interpret their signals. The light originating from K2-18b started its long journey before any of us came into existence. It traversed the immense void of interstellar space when humankind was still mastering terrestrial movement, containing within it the subtle indications of atmosphere, water, and the essence of life. When it ultimately arrived at our location, it altered our understanding of what it signifies to be human. We previously thought the cosmos was quiet and desolate, a vast domain to be mastered or comprehended. Yet Webb revealed to us that stillness can be misleading. The cosmos is not silent. It communicates through its chemistry in the varying proportions of gas and light, through patterns that suggest equilibrium and regeneration. Life, it appears, is not an exception. It serves as a natural mechanism for the universe to comprehend its own being. This insight transforms everything. It conveys that the demarcation between ourselves and others, between Earth and other realms, is more tenuous than we had envisioned. The very same processes that fostered the development of plankton in our oceans might be active beneath a crimson sun in Leo. The identical laws that sculpt the air we respire also fashion the clouds above distant, non-Earth oceans. For the very first time, our technology has attained a form of perceptive connection, a capacity to discern the presence of living entities without ever making physical contact. We are progressively learning to grasp life, not by witnessing its motion or development, but by discerning its cadence within the radiance of far-off stars. More revelations are forthcoming. More indications, some unambiguous, others vague. Every one will impress upon us that we are components of a significantly broader narrative. A narrative defined not by solitude, but by interconnectedness. And whenever a new world unveils its chemical composition, it will appear marginally less unfamiliar, and a bit more like a familiar dwelling. Centuries from this moment, explorers will one day stand upon the coasts of other planets. They will witness heavens painted by alien suns, oceans that never encountered our moon, and peaks that formed independently of our gravitational pull. However, amidst those vistas, they will discover something recognizable, the clear rationale of existence striving to endure. And upon glancing back towards the pale blue dot of Earth, they will comprehend what Webb commenced. That the pursuit of life was never solely focused on discovering others. It was fundamentally about self-comprehension, because within every spectrum, every calculation, every light quantum that traverses the vacuum, a universal truth resides. Life is not delicate. It is tenacious. It is innovative. It is the cosmos's most articulate manifestation of ongoing existence. The initial spark of life on K2-18b, the very first molecule capable of self-replication beneath a crimson sun, could well have been an echo of the identical fundamental principle that molded our existence. Distinct chemical makeup, yet the same core concepts of survival, adaptation, and consciousness. Upon that light's arrival at Webb's gleaming golden mirrors, a cycle spanning billions of years was brought to fruition, the universe contemplating its own existence, via the perception of one of its own creations. This is precisely what elevates this instant beyond mere discovery. It signifies a reunion. The stars no longer seem remote. They feel familiar, not due to our physical journey to them, but because we now comprehend their vitality. Consequently, the quest shall persist, propelled not by isolation, but by a sense of connection. Each new telescope, every mission, and every experiment will contribute an additional note to the identical subtle melody that links all forms of life. The cosmos was never truly devoid of presence. It was simply awaiting the emergence of something capable of observation, contemplation, and ultimate comprehension. Should you enjoy this video, please remember to give it a thumbs up and subscribe. Your support makes a substantial impact and aids the channel's expansion.